We are going to look at one-way analysis of variance, or ANOVA. We start with the general format for ANOVA table. You can see it here. We have the sources of variation, sum of squares, degrees of freedom, the mean square, and F ratio. We need to note that when calculating F ratio, we take the larger variance of these two and we place it as the numerator, and the lesser one takes the denominator side. We have this example. Given below are the number of customers who visited a commercial bank's ATMs which are located in 4 remote towns in a span of 5 days. So town A, this is the number of customers, town B, C, and D. We have to carry out an analysis of variance at 0.5 significance level to state whether there is a significant difference in visits among the ATMs. So the first thing we do is to come up with a hypothesis. So we start with the null hypothesis. It states that there is no significant difference in visits among the ATMs, and the alternative hypothesis is that there is significant difference in visits among the ATMs. Then we need to get our n. Our n refers to the total sample size. You can see we have 5 here, 5, 5, and 5. So the sum of those will give us our n, which is 20. Then we need to get our C. C refers to the number of treatments. We have 1, 2, 3, 4. So our C is 4. Then we come up with a table that will help us get the ANOVA done. So the first column here, X1, represents the observations from town A. So we shall take the values that we have for town A, this 84, 54, 70, 46, and 61. We write them here under column X1. Column X2 will represent the sample from town B. Then this is the sample from town C, and this is the sample from town D. Having done that, the next column is X1 squared, meaning we take the values which are in this column, we square them to get the values to write here. 84 squared, we write here. 54 squared, we write it here, all the way up to 61 squared. So those are the figures that we shall get. This next column is X2 squared, meaning we take the values in X2 column, we square them to get the values here. The first one is 70 squared, right here. 75 squared, you write it here, all the way up to 43 squared, which is this one here. This is X3 squared, meaning we take the values in column X3, we square them, get that, and then we take these values in X4, square them to get the values to write here. After that, we get the sums of those columns, the sums and these ones. So you add this, get this, all the way, you add all of them and you get their total. Having gotten those totals, then we can now start calculating our SST. We shall say our SST is given by the sum of squares of all items. The sum, meaning the total of squares of all items, minus the grand total, which you should square, divided by the sample size. So what we are calling sum of squares of all items means the sum of these ones here, the sum of these ones here. So that's what we have. You can see we have 27,9, 19,368, 22,511, and 19,451 minus t squared, the grand total squared, means you take these totals here, you add them. We have 315, 306, 325, and 307. Add them. It is their sum that you will have to square. So you get the total first before you square, and then divide by 20. When you do that, you will get this one simplifying to 82039 for this sum, minus, when you simplify this, you get 1253 squared over 20. and which boils down to 3538.55. That's our SST. Then we now start calculating our SSC. SSC is calculated by taking these totals here for the samples, the total for the individual samples. We square it divided by the number of items in the sample. So starting with the first one, the total is 315 and the number of items are 5. So we shall take 315 squared divided by 5. The next one is, the next samples total is this 306 squared divided by 5 because there are 5 observations in that treatment. Do the same for this 325 squared divided by 5 and then 307 squared divided by 5. Sometimes the numbers we have in the denominator change. Like for example, if we had 4 observations in X3, like we could be having 96, 66, 59, and 57 only, then we could have added we should have gotten the total, and assuming it is 325, we square it, divide by 4. So we divide by the number of items in the sample size. Now, when you simplify that, you'll get it giving you 46.55. Then we need SSE. SSE is found by taking the value of SST minus SSC, which I've done here, and the answer is 3,492. Having finished those calculations, the next thing is to bring our ANOVA table and we fill the figures. So the first one here was SSC, which we have calculated here and found to be 46.55. Then the next one here was SSE, which we have just calculated here, and SST, which was the first one we calculated. Its value is here, up here. So when we fill them, we get that. Now, what about this one? This one was C less 1, C minus 1. The number of columns we had, which are 4 minus 1, giving you 3. This one was N minus C. N is the sample size, which is 20, minus the number of columns, which are 4, you get 16. And then this is N minus 1. Our N is 20 minus 1, you get 19. Now, the next thing is to calculate the mean squares. And we get that by taking a value from the sum of squares divided by the corresponding value in the degrees of freedom. So the first one will be 46.55 divided by 3, and that will give us 15.52. The next one will be 3492 divided by 16, giving us that. Now compare the two and see which one is greater. You realize the lower one is greater, so we shall say our F will be 218.25. We have taken the lower one because we said we need the lower one to take the numerator side, then divide by the lesser one, which is 15.52, and that gives us 14.06. That is our F calculated. Now after getting the F calculated, we now go to F critical, and that's found by getting the value from the table. To do that, we need degrees of freedom. So we realize that the degrees of freedom 1, the first degree of freedom is 16. It should correspond to the value you have placed on the numerator side. The numerator side is this 218, and the corresponding degrees of freedom is 16. So that is the first one. Then the degrees of freedom 2 is for the denominator. This is the denominator, and the corresponding degrees of freedom was 3. So we put it as df2. And alpha, of course, we had been given from the question that it should be at 0.05 level of significance. Then we go to the table. Here is the extract of the table. You can see it's at 5% significant level. So it corresponds to what we have here. Now df1, which is 16, you look for it across. Here it is. Then move downward as you move across under df2. So look for df2, it is here, move across. The intersection of that gives you this figure here, 8.69, and that is F critical. So our F critical is 8.69. Now if we compare our F critical with the calculated value, which is 14.06, you realize that the calculated value is greater than the critical value. The calculated value is greater than the critical value. Therefore, we shall conclude and say, since the calculated value is greater than the critical value, we reject the null hypothesis and conclude that there is significant difference in visits among the ATMs. Thank you.